Yeah, okay, yesterday we stopped with this Belavin-Drinfeld theorem, which told us that the solutions under certain assumption to the classical Yang-Baxter equation can be classified into these three categories, rational, trigonometric, and elliptic. And today I want to start with the idea that Drinfeld had in 1985, namely to construct generic rational solutions to the quantum Yang-Baxter equation around Young's R matrix, which, as I have written yesterday, has had this expansion, and here this first order was the classical R matrix with this tensor Casimir here in the numerator. So it may be useful to make the distinction between abstract algebra elements and the representation a bit more explicit for the moment. So let me do this. So I want to consider some representation of my Lie algebra, and this statement here then more formally should look like this. And yeah, this R here is now no explicit representation anymore, but some abstract algebra element. And well, as you see, and as I already briefly indicated yesterday, the first order in this expansion here is given by this tensor product of Lie algebra generators, yeah? And Drinfeld's question was whether the higher orders can also be expressed in terms of other algebra elements. And this is what he tried.
So one solution is that all RPs are 0, right? Now
Yes,
thereafter
yes,
also
yes, exactly. And the answer is yes, and actually given by the Yangian. And just for completeness, let me, even though I mentioned this already on Monday in the seminar, let me give you once again the definition of the Yangian in the first realization. Given some finite dimensional simple Lie algebra, G, the Yangian is generated by these sets of generators, J and J hat, which have to obey the relations So this is simply the Lie algebra and these additional adjoint commutation relations for the level 1 generators. So this is what I call level 1 generator, and this is the level 0 generator. And in addition, we have the Serre relations that take this form. So this here means just total symmetrization, these brackets. So these are 3 level 0 generators, and I totally symmetrize them. And this ugly object here is a special contraction of structure constants. So this is 1/6 A I F B C J F C F K F I J K. And well, basically, this is how the generators are defined. I will give some qualitative comments on the meaning of this, of these Serre relations in a bit. And well, the point is we only have 2 different sets of generators, but if I commute J hat with J hat, then this is neither J nor J hat. So I generate a new level, which means that I get an infinite dimensional algebra.
So the way Yangian is defined here, does this imply non-trivial coproduct necessarily?
Does it imply this? I guess so, yes, because of this right-hand side. If you switch off the right-hand side, you have something like the loop algebra, like a loop algebra. But so I think. Okay, so the Yangian, I'm coming now to the coproduct. So the Yangian is a Hopf algebra, which I don't want to introduce in too much detail, but one of the properties of a Hopf algebra is that it has a coproduct, and a coproduct essentially for physicists is what tells you how to go from single-site representation to multi-site representations or multi-particle representations. And the Yangian has the particular coproduct, so for the Lie algebra generators, it's just the standard tensor product action. Yeah?
On a direct product, right? On the direct
Exactly, yes.
product.
So this is, here it's just standard, and the non-trivial piece is given for the level 1 generators. Sorry, this should be swapped. So J hat A plus H bar F A B C J C J B. So I always keep this H bar here. In principle, Drinfeld defines this, the Yangian as the algebra defined by these relations for H bar being 1. One can also rescale the generator so that one gets rid of H bar, but it's useful to see where the quantum deformation of this quantum algebra comes in. So this is a definition of the coproduct, which can be co-commutative or non-co-commutative. And you see that this term here makes it non-co-commutative, which means that the opposite coproduct, I tell you what I mean, is not equal to the original coproduct, and with opposite coproduct, I just mean that I permute the tensor factors. Yeah, so if, I don't know, for example, if delta is A times B, then delta op will just be B times A. Yeah.
It acts on this and this, and as opposed to this and this.
Exactly. And yeah, you see if I...
That's because of equities.
Yes, right. If I permute this, it's not the same anymore. And this is the reason, where do I put this? So this is why one calls this a quantum algebra or group, depending on your mathematical point of view. Yeah, it's this property, and that's why it's useful also to keep this H bar, because if you...
So you're saying the fact that it's not co-commutative, that's why we call it quantum?
Yes. It's, yeah, okay. It's nicely explained in these old Grünfeld papers, his motivation. I mean, he and Jimbo introduced this concept of quantum groups. He really says, okay, in quantum mechanics, or going from classical to quantum mechanics, we have functions that turn into operators that don't commute anymore. So I go from commutative to non-commutative. Now, then he motivates, okay, what's the analog of the quantum mechanical algebra for a group? And that's how he comes to this Hopf algebra structures. And then he says, okay, the quantization should mean I go to a non-co-commutative coproduct. Yeah.
By the way, all this coproduct business, I have a small confusion in that. So this coproduct, the way I understand it, is telling me how I should act on a direct product of two vector spaces.
Yes.
The usual action is that one, first action,
Mhm.
there is a fancy action. But now, the direct product, I can just perform that direct product and express it in terms of direct sum of some representation. If I have a two spin, let's say SU2 with spin 2,
Yes.
and I have two spins here and here, and now it's telling me how the J hat acts
Mm-hmm.
on these two guys, with one work first here, then here, and then together, like that. But now, two doublets, I can also think of them as a singlet plus a triplet.
Yeah.
And now I don't have a direct product structure anymore. So now, the way I would act on this space is simply by, because it's just a single site in some sense. There is a site, single site, it could either be a singlet or three states of the triplet, let's say. So how is this consistent with that kind of fusion of vector space? Is it?
So you want a kind of tensor product decomposition for Yangian representations. Yeah. That's
I just want to see that if I think of the direct product as simply sum over some representation, there I don't have a co-product to worry about because there is just one site.
But writing on the tensor having no representation, assume that the actions on two things is J tensor on one representation. So you're like the starting point for deriving on a first order equation. So if you put the new thing, it's not going to look so simple like that.
But at least from the point of view of the first guy, it is a single plus a triplet. But you're saying it doesn't make sense to act with the second, the level one guy on this.
I mean,
But
maybe,
sorry, if, for example, if you have a two-spin chain, yeah, and you do this decomposition, still you can, I mean, you can split it into singlet and triplet, but still you can write it as a two-side spin chain, right? The states in that that form these, and then you can act on these with this co-product.
But now someone tells me, so let's say there were spins, okay, and I started off with a representation where the spins were not doublets, but it was a singlet and triplet. Those were the spins. Okay. And then I act on this spin chain the way you tell me, and now someone tells me that actually that's single side. There is a small doublet there. Now should I now look further inside and modify the action of level 1 generator?
Probably, yeah, but I cannot tell. I don't know explicitly how this would be realized.
But how is it that if I choose to ignore, I'm getting different answers?
They were same thing earlier. Earlier it was just two different bases of the interface. Now, I mean, singlet triplet basis will still be there, but it won't have nice properties in the triplet surface. It is that way.
Is it not just a matter of writing the states in the correct form?
No. So what I'm saying is that you have a chain where each side could either be a singlet or a triplet. So four states.
I think
Now you act. You tell me how things act, and the way I act on these things. You tell me. But now at some point I realize that single side were actually two doublets together. So now I should act differently. Now the question is, okay, so now I acted differently. Now as far as the observables that I previously calculated are concerned, am I getting the same answers or not? The thing not, right?
I guess you can probably make this consistent if you dig.
So how do I know that there is some bound state structure?
Yeah.
I think particle singlet seems to behave differently than a non-particle. That's what we are. There's some different tag. So are there finite dimensional? So let's say I take the SU2 Yangian. Then are there finite dimensional representations of the SU2 Yangian algorithm? I mean, for example, is there some doublet representation of the SU2 Yangian?
Yes.
Just like for SU2 algebra.
Yes. Well, yeah, there are also some fusion procedures in this business of algebras. I don't know how to explicitly write this for the Yangian now.
If these coarse gauge observables that I computed earlier using the singlet and triplet basis, if they are going to be the same, even if I zoomed in and looked at these two singlets, two doublets, pairs on each side, then it seems to me that would be a satisfying input.
Why are we assuming that any tensor product replacement can be direct sum of the two?
Well, I'll just give you an example.
This is the usual case. Any tensor product replacement can be considered as direct sum of other representations.
Yeah.
No, I agree. This will not hold anymore for the Yangian then, I think. Yes.
So then this, yeah, so one more example of this. Anyone has the same structure.
Okay, maybe
Yeah.
we continue and discuss later. So for instance, if you look at SU2, yeah, and if you evaluate tensor product representation of SU2 and you ask for the constraints on a Hamiltonian, then you get identity and permutation, which are your SU2 invariants individually, right? But if you act with the, or for the S matrix, let's say, but if you include the constraints of the Yangian, then this will fix the relative coefficient between the two. Okay, so this is what Drinfeld defined, and let me now tell you in a bit more detail why he did this in the context of the quantum Yang-Baxter equation. And for this, I want to define a certain automorphism of this Yangian algebra, which I call boost automorphism. And I call it BU. And it should obey these relations, so applied to JA, it should give JA, and applied to J hat A, it should give J hat A plus U JA. Yeah, for some complex parameter U. So then Drinfeld wrote down a theorem on the relation of representations of the Yangian and representations of the quantum Yang-Baxter equation. And the theorem states that there is a unique formal series of this form. R of U is identity plus k from 1 to infinity rk. So exactly what I told you, with all these rk living in the product of two of these Yangians. And this R obeys certain properties, namely 1 times delta on R of U is R13 of U, R12 of U, and delta times 1 R of U is R13, R23 of U. And furthermore, this holds for all A in Y of G. So, yeah, let me explain a bit the expressions. So, well, this is what's formally behind these particular Hopf algebras. And you see already that in principle this, well, this here tells you how to go. This object naturally acts on 2 spaces, and the coproduct here turns 1 to 2. So this would tell you how to act on 3 spaces, and you see that you already get this factorized property that you then see in the S matrix in physical models. And here you have a relation between this opposite coproduct and the normal coproduct. And I will later make some comments on this for the S matrix. So the S matrix in 2 dimensions has, or asymptotic particle states in 2 dimensions have the property that you can order the particles, right? Because you have just one space dimension. And the in states are usually ordered with regard to their rapidities in the opposite way as the out states. Because in the in states, the left particle should be the fastest, and in the out states, they should all have scattered, and the right particle should be the fastest, yeah? And this is also why on the in and out states, you act with a different coproduct, because you have different order in the asymptotic states. And this is why you have the normal coproduct, and here you have the opposite coproduct. And now, this is the algebraic relation that relates these two in and out representations. Now I tell you already about the physical interpretation. And the relation is essentially given by the R matrix, which in physics will be the the scattering matrix. Yeah? So it basically tells you that these representations are equivalent, and the similarity transformation is given by the R or S matrix. Yeah?
Now there is no need to import the Yang-Box equation.
This is my next comment, I guess. Yes, that R of u satisfies the quantum Yang-Baxter equation. Furthermore, the expansion of R of u looks like this. So I write the log so that I don't have to write the 1 anymore and get a slightly nicer form. So this is what we had before, the first order. And now in the next order, we get J hat A times JA minus JA times J hat A. And then, yeah, you have higher orders. But you see that this exactly does what we asked for at the beginning, namely to express the higher orders in terms of some algebra elements. And the algebra elements are the ones generating the Yangian.
How are we taking this minus one? Is it that you take any two elements of the Yangian algebra and get the tensor product?
Where now? Where are you?
So let's say this like RU identity plus RK.
Yes, yes.
And RK is any element in the tensor product of
No. I'm just saying it lives in this space. Yeah.
Okay. And so how do you, what are the different properties of RK? Continuous to line?
Yes. This is other properties of this. Okay. Here I'm just using RK to write formally this expansion and to tell you that these elements live in this algebra.
So the minus sign comes because you want to satisfy this equation. How are you getting this particular negative factor to the equation? Because you want to solve this equation.
Well, yeah, since this is a unique solution, of course, it follows from these. I cannot give you now the explicit proof of this theorem.
This RU is an object which acts on two sides,
Yes,
right? And gives you two sides. Right?
yes.
Now, the first term is okay, you just act by J on both sides. And now there is a J hat.
Mm-hmm.
But now J hat is acting only on the single side. But I thought, I thought that the level 1 generator, it would be non-trivial only when it acts on two sides. Or also when it acts on single side. Because of the coproduct.
Yeah, I mean, it also has a single side representation, right? It has this J hat in front. I mean, J hat times 1 plus 1 times J hat, and then you have the bilocal piece.
Yeah.
So if I act with a coproduct now on this thing, I would generate.
Is it that J hat is actually just J?
No, no. You can choose something different. Like, for example, in the evaluation representation, you have U times J. It can be something else. Yeah.
But is there any, so at least this will be proportional to J, always J hat on a single side?
don't think, no, this is not necessary, I think.
So what sort of single site J-hat representations can be? I mean, how does J-hat act on a single site?
For instance, yesterday we talked about this generalization of, this formalism of formulating the Yangian on the action of any goods for, yeah, of Niklas. And there they introduce a local action which replaces one fermion by two bosons or so. So there can be more complicated things, yeah.
Is the boost metabolism automorphism has to do with the boost interface?
Yes, I mean, Drinfeld in his paper, actually it's only me who calls it boost automorphism, and I hope I can motivate why I do so. In 2D field theories, this is typically the Lorentz boost, yes. I will come to this, yeah. Drinfeld in his paper just says I define this automorphism. I add this name boost because it's better to remember, maybe.
But also another thing is that you say that this is a unique solution, but as a scientific, isn't this first term only is also not a solution?
Well, you could set this also to 0.
How? Where is the parameter?
No, you could set j hat to 0. You could set the single side representation to 0. Yeah. Okay, and in particular, if you have a representation rho, so this is, I distinguish here between the formal element and the representation, then this also obeys the quantum Yang-Baxter equation. Okay, two more comments. So this matrix R of U is sometimes called, due to Drinfeld also, pseudo universal R matrix. And unfortunately, R of U in this abstract way, if say I give you an algebra, can you tell me what R of U is? But it's generically not known. So I cannot simply say, okay, give me an algebra. I write you down what the universal R matrix is, and then I.
But you just wrote the solution, right? I'm saying the series completely is not, the whole series is not known exactly. Because you know the representation of the Yangian, I thought you just wrote down the solution.
No, I don't think. I don't think you can simply write down the whole expansion explicitly. So actually, in order to determine what this thing is, there is a useful additional theorem which basically tells you how to construct a representation of this thing. And the statement is that this R rho of U being rho times rho R of U can be obtained from the following constraints. So we have the level 0 constraints, which are simply your Lie algebra constraints. and the level 1 constraints, which look like this. And this should equal a similar thing on the right-hand side. So you see here you can specify the single side representation. This you can still choose. Still you already have this shift here. And yeah, this is the algebra symmetry, and these are additional constraints. And for instance, if you look at SU2, in the fundamental representation, so my G is SU2, and I take as a representation rho of JA, and well, in the following I will stop now to distinguish this between representations and these abstract elements. I might mention it at a few places later. It's sometimes useful, but here it's not so useful. It just takes more time. So this is just the Pauli matrix. Let me divide it by 2i just for convenience. And for j hat, I simply choose the single side representation to be 0. And then I want to write down an R matrix. So at level 0, yeah, as I said already, I just have the standard SU2 symmetry, which tells me that the R matrix has to have this form. So I have some coefficient of U and V times the identity plus another coefficient of U and V times the permutation operator. Yeah, so these are the only invariants under this tensor product SU2. It's you say it's a function of 2 parameters now. Okay, here I have 2 different parameters, yeah, which are these evaluation parameters for the first. I mean, I have a 2-side action. It's a parameter on the first side and it's a parameter on the second side. These can generically be arbitrary. I can show using this constraint that I can rewrite this just as a constraint including the difference of U and V. So in principle, this is a bit blown up. It can only depend on U minus V. It will be U minus V, yes. But a priori, with these constraints written here, I don't know this yet, right? Here I just want to say, okay, I have 1 parameter for the first side and 1 parameter for the second side. So I do this generically, and well, now one can really sit down and plug everything here in, the Pauli matrices. Yeah, I set this to 0. This is essentially a Pauli matrix. These are Pauli matrices. And I commute or I evaluate these constraints given this solution to the level 0 symmetry. And what I find is that R of U and V has to have this form. So it's 1 plus 1 over U minus V times the permutation. So this is again Young's R matrix that we had seen before. Yeah, so you see SU2 gives me two free coefficients, and these Yangian constraints fix also the relative coefficient. It remains one overall function. Yeah. So yeah, I could do this more explicitly, but it's really taking the Pauli matrices and plugging them in.
Now, I mean, so this is one, but the solution that you had written down,
Yes.
even there, if you just substitute J hat equals 0, this is what you get.
Yes. Yeah, that's true, but this is also a very simple example.
A remains undetermined.
Remains undetermined. One can also make include the crossing equations into this Hopf algebra business, and usually one uses this mathematical form of the crossing equations formulated in terms of the antipode of this Hopf algebra to fix this parameter. But yeah.
So that fixes with the A also.
One can fix it with this, yes. But yeah, it's also some more work. Okay, so now you have an idea how the Yangian enters the or relates to the quantum Yang-Baxter equation.
So is this the unique two-dimensional representation of Yangian?
I don't know.
Just in the case of SU2, if I asked about a non-trivial representation, you'll be able to say a non-trivial representation of Yangian. SU2 Yangian. I mean, I understand that even the trivial representation has this power, and one can just fix out everything because of this theorem that says that there is a correspondence, one-to-one correspondence between the representation of the Yangian and the R matrices.
Yes.
Satisfying the quantum Yang-Baxter equation. So even the trivial representation would give you a non-trivial solution, Yang solution. But I wonder, and this you are saying is only rational, only for rational.
Only rational, yes. Yangian is only rational, yes.
So, I mean, presumably theorem would be more contentful if there is a non-trivial representation, and then I will find another solution.
Well, there are other solutions, but I mean, okay, I could also use SUN here. Actually, it gives me the same result. This doesn't matter, but what?
I just want another rational SU2 argument.
Another rational.
You can use any dimension, let's say.
Okay.
Does there exist one, or is it the only one?
No, I think it should exist. I don't know how it looks like. But I think you can apply this. Yeah, I just chose this example because it's really, probably everybody has known this before, and it's very intuitive.
This replacing rho of J hat to be just J will not help, right? Because that's just the automatic.
This will not. This will just impose once again the level 0 constraints. Yeah. Okay, let me just make some comments on representations and the Serre relations.
Seems that it is more appropriate to call a Drinfeld.
Well, Drinfeld writes in his paper that in honor of Young's first rational solution to the Yang-Baxter equation, he calls it Yangian. There's also a Drinfeldian, actually. Yes. So this came afterwards, I think. Usually if you you invent something yourself, you cannot name it after yourself, right?
So someone else should have done
Someone else would have done
that.
that, but he did this already before in his paper, so. Okay, the idea is that the co-product should have some nice properties, and in particular it should be an algebra homomorphism. So basically what it should do is to commute with this bracket. And well, this is not so difficult to see for, well, now I call the elements A and B and also the indices. I hope this is not a problem. If both are level 0 generators, and it's also not so difficult if both are, if one is level 0 and the other one is level 1. But it's not so simple for A, B being both level 1 generators. So the question is, what is this thing here? Yeah. And I told you before that this will neither give a level 0 nor a level 1 generator, but it will give a new element. So answering the question what this is also answers the question what is the co-product for the level 2 generators. Yeah, so it gives me some information on the higher levels of the Yangian generators. So the idea is that what one can say is that the left-hand side of this equation here transforms somehow in the adjoint times adjoint, because here I have two adjoint indices, and because of this bracket it's anti-symmetrized. And this has the form adjoint plus something else. Yeah, and well, it seems natural that that you require that the level 2 generator also transforms in this adjoint way. And in fact, this is exactly what the Serre relations do. The Serre relations furnish a sufficient criterion for this vanishing x here. Yeah. So this just to motivate why there was this rather complicated additional relation. This is the idea behind. So this algebra should have nice properties. In particular, this delta should do this. And for two level 1 generators, this is not straightforward. But these Serre relations that I gave you are sufficient to guarantee that this transform nicely, namely that only this remains and the x component here vanishes.
Why do you insist that the level 2 generator has to be an extent? Allow for
Well, I guess this is part of the this is the Yangian, right?
I understand, but what required me to have, I mean, for the second level generator to be end of? Why would
I think this, for example, yeah, that you want something like this.
No, it could still work. I mean, you can just write del J hat A, J hat B equal to del J hat A, del J hat B. The right hand side will also belong to adjoint plus x.
Is it clear that one can construct such an example? Yeah.
I don't know, but why not allow for
Well, sure, you can also drop the cell relations and say I have an algebra with these two sets of generators. I just think they're
If you decide to go with this co-product, the charge relationship and office is not necessary. And if charge relations are assumed, then this X is anything as it is. It's all sufficient, not
yeah, I guess otherwise you define a different algebra that you can investigate, and I think at some point you just lose some nice properties. I don't know where exactly, but it's a different algebra. Yeah. Yeah, and in particular, since many of these things are abstractly formulated, and it seems okay, I can just always lift my. If I do this, I set this to 0, and I just take a Lie algebra representation and I plug it in. Yeah, my coproduct then tells me how the Lie algebra, how the level 1 generator can be expressed in terms of this Lie algebra representation. You would think, okay, I can take any Lie algebra representation, but this is not true because this is not satisfied for any Lie algebra representation. So there are constraints on the Lie algebra representation to lift it to such a Yangian representation.
So is the adjoint of G or YG?
The
There will be an adjoint in the adjoint of G or adjoint of YG?
adjoint of G, I guess, yeah. Yes, I think so.
By the way, is that you won't call this Jacob ideal with X?
It's how's it called?
I'm just wondering because with that this vanishing of this Jacob
Yeah.
ideal appears in some other places also. I just wondering whether it's the same.
I don't know how this is called. So you mean this form of the cell relations?
No, X.
Just X, okay. And it's not related to Yangian algebra.
Yeah,
Okay.
totally different.
Okay. Which context?
Some constraint on the Higgs branch, for example, of symmetric theory.
Okay. Non-integral. Or integral. Because if they're integral, maybe it's still related. Huh?
So what was the remark about the other representations? So you said that if you take spin half representation, then that's the story about the level 0 and level 1. Right?
Okay, I think this might become more clear when I say this here. So I want to make some comments on the evaluation. Representation. So, given a representation rho of G, I can choose rho U JA to be rho of J. Yeah, so my level 0 rho U is what I call now evaluation representation, and for the level 0 generator I just choose it to be the standard representation. And rho U of J hat A I can choose to be U times rho of J A. And this is a standard way of constructing representations, and these are also the representations that play the important role for the S matrix. Then this will be the rapidity of the particles. And in order to show that this is a valid representation also of the Yangian, I have now to show that exactly this this X part of my right-hand side of the Serre relations vanishes. So if I make this choice and I look at the cell relations, I find that the left-hand side of the cell relations vanishes. So I have to show when projected on this X, so I have to show that also this vanishes. So
X will be direct product of adjoint times adjoint. There you are taking some symmetrized product of three adjoint.
Right, there is one.
Yeah, yeah, but if I thought you are just motivating it from this equation
yes.
without actually writing the relation. So
Yeah.
from that relation, it seems that what you are imposing to be zero is some part of the antisymmetric product of two adjoints.
Mm-hmm.
While over here, you are imposing some part of the symmetric product of three adjoints.
Do I need the X projection? I think I do. Well, if I plug this into the cell relations, will the left-hand side be 0 without projection?
No, I mean, if I just begin this way, that the delta J hat A, J hat B computer
Yes, yes, yes.
should be an adjoint.
Yes.
Uh,
No, sure, this
then
is
should I should just take this and put it there, and that would follow.
right. This is
This clear now.
yes. I just wanted to make more explicit connection to the cell relations, because now this you can explicitly put into the cell relations, and you see, I think, that the left-hand side vanishes, has no adjoint component. I think this is the statement. Has just an adjoint component. This one. So for consistency, the right-hand side has to obey the same constraint. And this does not work for any representation rho of the Lie algebra. So I can only do this for some representation, not for all. Yeah. So
Who are we goes like X vanishing?
yes, now I just want to say again, if I have to impose that X is vanishing, but this corresponds to the cell relations. Yeah. Here I just want to say more explicitly, if I now choose this particular way here of constructing a representation of the Yangian, I can plug this in. Now I have made a special choice for my level 1 generators. I can plug this into the cell relations, and I see that the left-hand side of the cell relations will vanish under this projection. So the right-hand side has to do the same. The left-hand side vanishes in a simple way, but the right-hand side not. And this is what gives these additional constraints. And it's the same as imposing here that the X vanishes. Yes?
So we need to check that the left-hand side and right-hand side are same on the adjoint surface. The LHS is not 0 on the
I think they don't have a...
Is it like automatic closing assignment or?
Okay, let me check this explicitly afterwards. Let me try to evaluate what the statement is. Yes, I mean, yeah, I can plug this into the cell relations and see what I get. Yeah. Okay, the statement here is just that this gives constraints on the representation of the Lie algebra rho that can be lifted to such a Yangian representation.
Could you tell us what is the
It's, well, what I wrote here, for example, that you need that this projection vanishes. It's not easy to show. It's not, I mean, there's nothing.
No, but that did not make any reference to the algebra representation. That was some algebra relation. Now we're talking about the representation of that algebra, right?
Yeah, but this will.
So, when carrying this out, what kind of constraints?
But this relates to this thing, right? It's the same
Yeah.
thing.
I understand the constraint follows from that.
Yes.
That constraint, but what is it in concrete cases, let's say for SU2 or SU3 or SUN? What kind of representations can be difficult? What kind of representation cannot be?
There is no general classification. I think Drinfeld's statement is that he found examples for all algebras except for E8 or something like this. If you look how to show these things, it's very ugly. You can, for example, for the PSU 22/4 representation on the dilatation operator, it was shown in this paper by Dolan, Napi, and Witten, and it's a very long computation.
What I'm saying that you're saying that just this consistency requires me that my single site representation of the Lie algebra should be constrained. If I know what these constraints are, and then if I see a spin chain with that representation there, I would be immediately able to say without doing any computation that this is not going to be integrated. Right?
Yes.
So what I'm saying, what I'm asking you, what kind of constraints are these?
I don't know, this.
So
Ta-
is spin half a solution?
Yes. Yes.
But there's no listing of the other.
No. There's no general classification of this, I think. No, this is some parameter. It's a complex parameter. Mhm.
Okay, one question also. You define X from the antimatic product of two adjoints. Suppose rho is a really big representation, much bigger than that. What is X to?
I don't know what X is explicitly. It's the rest.
How do you define X? Oh, you're saying that
It's
take the row, plug it into the left hand side of the circulation, it will be you have an adjoint part and
Yes.
everything else.
Yes,
X is everything.
exactly. Everything else.
Oh, so this is not the same X as on the left hand side of the circle. Left side of the row.
No, it should be the same. Yes.
This is the non-adjoint part of some arbitrary product of some. It's a non. X here is the non-adjoint part of the product of two rows,
Yes.
right?
Actually, on the left hand side you had X appearing in the direct product of two adjoints, symmetrized product of two antisymmetrized product of two adjoints. You said that product will generically be an adjoint plus X. I can't be clear that X belongs to that because that is a symmetrized product of three adjoints.
Mm-hmm.
Right?
That X be.
It's not even clear to me that X will appear there.
Okay, then you've shown it already, right? Then you've shown. If it does not appear, then you've shown that the projection vanishes.
The symmetries of that relation and the symmetries of this relation are different, right? Because we take JAJB and we take the anti-symmetric tensor
Yes.
and here it's a fully symmetrized, so it's not clear.
No, it's not clear. But if it does not appear here, then you've shown that it's not there, right?
Why
That-
is that the same thing as spin? I mean, if I take 3 cross 3 anti-symmetrized, then I'll have a 3 on the other side. And in a normal
Yeah. So X is 1 plus 1.
sorry, X is 1 plus 5, but then 5 is out because I'm taking anti-symmetrized.
Yeah.
And 1 is also out.
So 5 from
it's it's the same x, and yeah, if it does not appear there, then good, then you have then you have shown that it vanishes, right? Well, yeah, this is actually what you want, right?
It seems like something one should be able to evaluate and see what are the constraints. Some simple thing.
Possible, yes. So how do you do this? If you don't specify the representation, yeah?
Yeah, you take a particular representation, just evaluate this.
Yeah, but for particular, you wanted to a general criterion, I thought. no?
Yeah.
So if you don't have take a
What I'm saying
particular,
is some Lie algebra exercise.
yeah, but an example or a general one? That's the question.
In fact, I would be satisfied even if you tell me an example where this constraint is not satisfied.
Okay. Yeah, I guess for E8 you find.
Then you're now telling me Lie algebra. I thought you were going to tell me a representation.
I guess then you can take probably any of E8.
Okay, so I'm completely confused about what X is here. Okay, so let's take rho to be the spin half representation of equation. We know what half tensor, half tensor, half is. Right? Can you tell me what X is?
I don't know. I have to think about it explicitly. X should be defined by what I wrote here. It's the rest once you take away the adjoint. Adjoint plus whatever remains.
I take half tensor, half tensor, half the midrest thing, remove the adjoint, whatever is left is X.
Yes.
But not in that. I thought this was
Here it was.
joint and
It
adjoint
can't be both.
and symmetry. So you said that X should
Here,
be
what was written here? Adjoint, adjoint. This anti-symmetrized adjoint, adjoint.
So I take adjoint, one tensor, one antisymmetrized,
Yes.
and then remove the adjoint, or do I take half tensor, half tensor, half and remove the adjoint?
No, you take this anti-symmetrized. What was written here? You take.
That one.
Yes.
Okay.
X is the that's what.
And like, exactly. Yeah, I
So
thought
that's
you
why
just
perhaps
put
for SU2 there is no constraint because we know that there is a spin shift for every Yes. Right? Every you can have any
Okay, some more general comments just to, because in the context of the Yangian, this is a bit subtle, so let me say something on quasi-triangular Hopf algebras and, okay, let me do this. So, given some Hopf algebra I, one says that this algebra is co-commutative almost co-commutative if an element R living in A times A, and this is my Hopf algebra, such that my opposite coproduct is R delta A R to the minus 1 for all A in capital A. I have another property called quasi-triangularity, which means that I have an almost co-commutative pair A and R, which obeys similar relations as I've already written down. and then R is called universal R matrix and obeys the quantum Yang-Baxter equation. So why do I write this? Actually, because the Yangian does not exactly fall into this class, but it only fails for subtle reasons. That's why it's sometimes difficult to see why it does not belong to these. So the Yangian is not quasi-triangular well, but something that one could call pseudo-triangular. Which is due to the fact that it's not exactly this relation that's obeyed, but what I've shown you before. So we had like BU times 1 delta op is R of U BU times 1 delta R to the minus 1 of U. Yeah, so you have this additional boost automorphism that enters this relation. And the point is that I cannot just take this whole thing as my R matrix, because this does not live in the Yangian product, tensor product. It's only this thing. And this is why it's strictly speaking, not a quasi-triangular Hopf algebra. And secondly, let me say that the Yangian is a quantum deformation in the sense of quantum algebra or quantum group of the universal enveloping algebra of the polynomial algebra, or half of the loop algebra. So this just as a side remark. So if I take in these relations that I've written down my H bar to 0, I get the universal enveloping algebra of this half loop algebra. So in this coproduct, this bilocal piece actually drops out, which came with this factor H bar. And yeah, the level 1 or level n generators will essentially be something like u to the n j, which is this loop algebra. So this is just about a bit about the context. Well, this is maybe important to emphasize because sometimes it's not so clearly stated in where the Yangian actually belongs, and yeah, I guess this is anyways interesting to see what happens when H bar goes to 0. Okay, just a few comments on Yangian symmetry and the 2D S matrix.
Sorry, polynomial algebra is what is the product of generators?
So this it's generated by generators of this form. So this is a Lie algebra generator, and I put in front powers of this parameter. Yeah.
Don't see how if we see that h bar goes to 0, the Yangian simply becomes universal enveloping algebra of that.
Can you see this?
No. So the Yangian, I guess you think of it as the first realization that we do, right?
Yes. So the right hand side of the Serre relations
Yeah.
vanishes, and yeah, this is basically something like the evaluation representation here, yeah? Without the bilocal piece.
Well, how do I get, for example, how do I get so universal enveloping algebra would mean you have products of generators and so on, right? For example, in the SU2 case, you would have J times J and J times J, so on and so forth. Or a product of
Or tens of products, yeah. Yeah.
This product.
Um,
On the same side. That's universal enveloping algebra, right?
yes.
So
But
how do I see that as h bar goes to 0? Because one representation of the Yangian was when the level 0 generator was taken to be 0.
the level, this one side representation of the level, yes.
And there if I take h bar to be 0,
Then you still have this automorphism that can induce this parameter, I guess.
but still a linear NOP, right? Not all products of J will come. Will they? I don't know what happens at second level, level 2 generation and so on. Should I think of the Yangian? So I can stick to thinking of the Yangian as something that is acting on single side, right? And the rest would be covered by co-products and so on. So let's just look at the single side. Now at the single side, the universal enveloping algebra would mean action of all products of generators, and I just don't see those things.
How is this? Okay, I think I have to think about this. It's not clear to me at the moment. Okay. For the Yangian, in the context of the S matrix, as I already mentioned, in 2D I can order my asymptotic states so I have states U1 to UN, and well, I can order the rapidities, which is again very special to 2 dimensions. And then the S matrix will relate my in and out states. So depending on conventions, people often write that the S matrix acts on the out state and gives the in state. Well, and then the S matrix is exactly this quantity that obeys these Yangian constraint relations. Yes, but this seems to be the convention most people in this 2D literature use. I agree that it's unnatural, yeah. So it obeys these Yangian symmetry constraints, and in a form like this, so delta A comma S is 0. And for the S matrix, I can write this nicely like this, because the two-particle S matrix, so S2, 2, 2, is actually because of the fact that I have now these ordered in and out states, and I swap the order in going from here to here. The S matrix is actually the permutation times the R matrix, or representation of this special pseudo-universal R matrix, and therefore obeys the quantum Yang-Baxter equation with slightly more modified indices to what I told you before, because I have to multiply the R by the permutation operator. This will just change the labels 1, 2, 3 a bit.
This is actually the T matrix. There's also the identity one, the forward stepping, which nothing happens. Your S should be like 1 plus, not 1 plus.
But why can this not be included in this? I mean, this is a
that also is a 1 plus T, then T times T, that will be 1. I mean, I'm saying that S has to have a 1 in it, isn't it, or not? Is it?
yes, yes. But the 1 will certainly also be a solution to my symmetry constraints, right? 1 will be invariant under symmetry. So like in this SU2 example, it was 1 plus permutation. These were exactly the two cases.
That was 1 plus permutation, which was the solution for R.
Yes. Now I permute it. Now I add this permutation operator, then I have permutation plus 1 instead of. So, yeah. And yeah, as I already indicated, one can check explicitly that the Yangian constraints that I've shown you imply that S of u comma v is S of u minus v. So the standard Yangian invariant S matrix has to be of difference form. Yeah. Okay. So this about the formal aspects of the Yangian. Of course, there's a lot of mathematics behind, and I think this theory of the of Yangian representation is not very well explored. At least from a physicist's point of view, there are also some mathematics papers, but I think there can still be a lot done. And yeah, like you're asking general questions for classifications of representations, I think there are just no answers for this at the moment. Second, well, what is first and what is second?
H2 to 3 you said is completely fixed, or what was it?
This?
Yeah.
This just says that the S matrix, 2 to 2 S matrix, is given by the permutation operator times this R matrix that I've talked about.
Right, and so what is this H2 comma B? Is it for?
This is the 2 to 2 S matrix, yes. So the 2 to 2 S matrix can in principle depend on the on two rapidities, yeah. Yes, in principle it can depend on 4, yeah. In and out could all be different. But the Yangian assuming I have two different, like I did in these constraint relations, only using these Yangian constraints I can show that the S matrix has to be of difference form. It can only depend on the difference of rapidities.
Doesn't it follow the different levels in the identity? Because if I go to the center of mass thing, then the two rapidities will be just the opposite.
Exactly, and that's also why I call this boost automorphism.
Yes.
Well, if you just come abstractly from the Yangian symmetry, yeah, you have these constraint relations, and only from these you find this. Of course, if you're in a Lorentz symmetric theory, this should follow.
So if U and V are really boost parameters, then it's obvious, but if they are the more abstract.
Yeah, but, yeah, exactly.
So is the second line not coming from that given the S matrix, given this follows from there or not?
It's, yeah, this is a statement about the R matrix or the S matrix. Of course, it's the same. If I say the R matrix has to be of difference form, this implies the S matrix has to be of difference form. Sure. I just wanted to emphasize that suppose you just know the Yangian symmetry and don't know anything about Lorentz symmetry, this is already implied. Yeah, and actually this is what I quickly want to comment on again, how to make connection again to the field theory. So how about quantum charges and the Yangian in 2D? So you remember this classical definition of my current, J mu A of x yeah, so this was my classical current. So if I now want to say, okay, this should be my current in the quantum theory, as I already indicated before, I would get the problem that generically here this would be divergent, and I would have to look at the OPE of these two products. So generically this operator product divergent. So I would like to regularize this, and I should do this in principle by looking at what this product gives me generically, and I should look at somehow at the OPE expansion for these currents, but then again, usually I would have to specify to a certain model and look at what I get. One can make some rather generic assumptions, and then mainly Lüscher has shown that one can fix the form of this OPE quite well, so one can find a rather generic expression for these divergences. I don't want to discuss this in detail. Let me just say that the idea is to introduce some point splitting and to define a current J mu A t comma x depending on some parameter delta. Now here with some function z of delta in front of this local term. And here my integral should now just run from minus infinity to x minus delta. Yeah, so that I, in this limit of delta being 0, I get this divergent piece. Yeah, so here I now introduce some renormalization constant. And yeah, the idea is then that I define my regularized current as this limit of delta going being 0. And yeah, I can do this explicitly, for instance, in the context of this Gross-Neveu model. One can find explicitly what this delta will be and how this regularization looks like. Maybe I quickly sketch this. So, for example, for the chiral Gross-Neveu model, I have that my z of delta will be g square c, which is the Casimir of my SUN generators, and then I have some log mu times delta plus terms of order delta. This mu here is now a mass scale that I introduced in the quantum theory, and this mass scale actually generates the masses of the fermionic particles. Yeah, one can also go through this in more detail. One would really have to look at what is the OPE and how do I get this. What kind of divergence do I pick up that I want to cancel here, and I find that I have to choose this function.
The divergence somehow is only proportional to the J, not to any other operator. So that means
Yes.
the OPE only consists of one term.
Yes. And in this theory, it seems to be like this. And actually, there are not many examples where people have done this explicitly. There's this Lucia paper and one or two papers where this was generalized to other theories, but in these theories, one assumption was actually that, yeah, essentially there's only this single current in the experiment.
Conformity is invisible, but here okay, I don't remember what happens to it.
It's still if you consider Gerasimov multiple. But if you just look at conformity with the
if I have JJ, then
it's a conformity, it's a reasonable.
yeah.
Maybe it's J, but when you think of them as Gerasimov dependent, right? But if you just think of them as conformal dependent, you're finding conformal, but then you would have multiple states like this. And I'm just saying that decompose all these representations into small representations. I mean, here you don't even have a global conformity.
Yeah, here it's not clear to me because
No, I don't think it's obvious, but this is the result that you get.
C is what?
C is the Casimir of SUN. But
yeah, that would seem to suggest that I'm taking JJ equal to A to B C and therefore the sigma is C squared.
Yeah.
But,
So
Big.
only like current
it is like
yes.
But we are talking about the when
Okay, so let me maybe for today make one final comment related to this to this boost. And this is actually quite nice because it shows how these algebraic properties, as we already said before, the Yangian implies already this difference property, and from a physics point of view, this would correspond to Lorentz symmetry. So how does this now fit here into the picture with these currents in my 2D field theory? So if I look at the Lorentz boost, which is this operator here, and I act with it on my current, then the action is given by this. And well, it's relatively straightforward. You remember the level 0 charge was just the integral over the 0 component of this thing here. Yeah. So I can also integrate this relation and compute what the boost does with the charge, and it's relatively straightforward. To see that you get a vanishing commutator. So the boost commutes with the level 0 charge. Yeah? Just to understand which algebra we have. So the next question is, what is the commutator of the boost with the level 1 generator, the level 1 charge actually. And to do this, there's a nice graphical argument by Bernard. So what I want to do is to define or to look at a bilocal current in the same form as before. But so far I've always integrated over the x coordinate, right? I've always been on the coordinate line. In principle, since I have a flat current, I can also shift my integration contour. So I want to look at a bilocal current with a generic integration contour. And this contour I call x minus delta due to this point splitting that I did. So I write the current J mu A of t comma x delta as z of delta epsilon mu J A mu with its arguments minus 1/2 f a b c j b mu x integral epsilon rho epsilon sigma rho dy rho j c sigma of y, and now I integrate over this generic contour. So let me draw some picture for this. So this thing here corresponds to such a picture. I have Tx and I integrate over some contour gamma x minus delta. That, I mean, before I've always integrated here over this half line up to the point x, and now, or x minus delta, and now I integrate over some deformed contour that I can do because the currents are flat. So now the schematic idea is to do a finite boost transformation, which in the space just corresponds to a rotation. Yeah. So I do a finite boost transformation bu e to the ub with parameter u being just 2 pi I. So this should be a Euclidean rotation by 2 pi. And in principle, we now look at the Euclidean case, here's my point x minus delta, or x minus delta, and here I have a point x. Then what I do is to wrap this contour here once around this thing. And x is actually now the coordinate of this current here in front, yeah? So this is an integral over a contour from somewhere in the negative infinity to this point x minus delta that I've written here.
Your final J is at part X.
My final,
Is
yes.
so the contour that you are defining is the X integration contour or Y integration contour?
Y integration, yes.
Why are you allowed to do that?
Because the current is flat.
Because there's a flatness condition. So we can contour anyway is very given. Earlier the contour was all along the x-axis. Now it's something like that.
It's not because current is not the charging contour. It's because of something else.
Because of the flatness.
I had these two conditions for classical integrability
It's because of the flatness of the current you are allowed.
allowed to shift, yeah. So before I had the contour here on the line, and now I shift it to somewhere else. I do this finite boost transformation, which means to wrap this contour around. And now I can rewrite this slightly. Here I take my x minus delta. Here I have my x. And now I want to do the integration in this way. Yeah. So doing this is motivated by the fact that now here I end up again with my original integral over the contour gamma x minus delta and some how did I call this? Some circular contour small gamma around the point x. So this means what I did now was my boost transformation on my current j hat mu Ex delta, and what I get is my original current, because this is simply the integration over this contour here. Minus 1/2 FABC, and now I have a circular integral here. Of this type, and well, now the idea is again, I would have to look at the OP explicitly. This integral will pick up the pole, and yeah, if you do this explicitly for these models like the Cairo-Grosvenor-Will model,
But you don't have to look at OP, like just the action of the charge on the current, so you need to use the algebra to write that as J8. That is the charge acting on current, right?
okay, but why do I get a finite contribution then? If it's not divergent?
No, I mean this is how you measure charge, right?
Yes?
You just integrate the current, and there is a charge inside, and what it measures
Yes?
is the charge.
Okay.
We got the semi-pole. We got the semi-pole.
Yeah, you could do it by OP.
Then,
Yeah.
then it's a,
Okay,
as
mhm.
we said, you just pick up by the residue another, say, FBC.
So what one finds, this is for the charge, is this is the original level 1 current minus, and here the prefactors are again this Casimir times the level 0 generator, yeah? So well, now I did this transformation with the parameter 2 pi I. In general, what I have is something like, so let me take some parameter u hat, j hat a. This will give minus c u over 4 pi I, if this is my u hat. So you see that up to some prefactors, this is exactly this parameter of this boost, and this means that this b u hat is my boost automorphism that I introduced before. So you see, this arises really in the quantum theory. In the classical theory, the Poisson bracket of these two will be 0, but in the quantum theory, you pick up such a pole and get a non-zero result. So if I have a two-dimensional field theory with Lorentz symmetry and an internal Yangian, this is what I looked at here, I now have the algebra P mu commutes with JA, and it also commutes with J hat A. And I have that the boost commutes with the level 0 symmetry, and the boost does not commute with the level 1 symmetry, but it gives me the level 0 generator. And this is actually quite important, because this gives much stronger constraints on, for example, the S matrix or so, than the direct product of this internal and the Poincaré symmetry. Yeah? And okay, here we're in 2 dimensions. This is exactly where Coleman-Mandula does not apply, but in principle, their statement was that in higher dimensions, you can only have Poincaré times internal symmetry. Yeah? So you see here in this 2-dimensional example, you have coupled these two symmetries. You have an algebra that's intertwined in this way. Okay, that's, I guess it's very late already, yeah. So sorry that it took so long. That's it for today. People have already left. So.
So if you have, in addition to the Lorentz symmetry, conformal symmetry, Virasoro symmetry, and so on, so those symmetries will also have non-trivial commutations with the level 1 Yangian?
Well, I think it really depends on your theory. This is realized in a few theories, like this Cairo-Grossman-Bull model. Do you have a particular example where you have Yangian symmetry and?
No, I mean the statement that the boost with J hat equals J
Yes.
is a general statement, doesn't depend on the graph medium. This is a statement about Lorentz invariant quantum field theory symmetry. The ones that have Yangian.
If these arguments here go through in the right, if the OPE, if you can regularize the current, so if it survives quantization, the symmetry.
So if you have additional
Yes.
symmetries that have non-trivial commutations with B, probably some Jacobian integral would mean that J hat should also have non-trivial commutations with those. So something like that. That's a special conformal transformation.
Yes, but do you have any concrete example in mind that could fall into this?
Conformal symmetry, the integral of this conformal. It's okay, it's a very good question.
Well, sure. If you have further further algebra relations, you can just check what you get. But I'm not sure this exists. So.
Because yesterday or the day before there was some discussion about the conformal case, the W symmetry somehow being. Yeah, so the integral
Yeah, but there I think it's much less straightforward how the Yangian enters. I think it's already really not easy to see this. How this Yangian is embedded into this W algebras. Yeah, I'm really not an